Look at this presentation. So these are all the things what we have seen earlier. So up to the calculation of the normal pressure and the normal temperature we have seen in the last class. Today we are going to see a very important lesson. It is the teaching on ideal gases. What is an ideal gas? How this ideal gas equation was derived? What actually an ideal gas is? How do ideal gas and real gas differ? What are the important characteristics of an ideal gas? These are all the things we are going to discuss today. Look here. When I taught thermodynamics in the second year, very often I have told you the mass, the pressure, volume, and the temperature. When you define the values of these four entities, that definition will give you the state of a system. What is the state of a system in thermodynamics? A system, it assumes a particular state where the mass of the gas confined, or the pressure, the volume, and the temperature, they are all given a particular value. That is the state of a system. If any one or more than one entities among the four change their values, then we can simply say that the state of the system is changed. If these four entities have a constant value with the time, when time changes, if their values do not change, then the system is said to be in equilibrium. Now the question is whether mentioning the values of all the four variables are necessary to describe a system. Certainly not, because if any three are mentioned, the fourth one can be calculated because they are all interrelated. That is the understanding. So later on we will discuss what are dependent physical parameters or independent parameters. We are going to discuss a little later. So having this thermodynamic background, that is the mass, pressure, volume, and the temperature, which define a state of a system, and when they remain constant with the time, then the system is said to be in equilibrium. Then having all these things as the fundamental understanding, three scientists proposed three different ideas about the gases. First one is Robert Boyle. According to his observation, volume and the pressure are inversely related at a constant temperature. So this proportionality is mentioned like this. Volume is inversely proportional to pressure. So this can be made an equation. Volume is equal to a constant into 1 by P, which is represented as volume is equal to C by P. Or I can write, if I bring this pressure to the left hand side, PV is equal to a constant. So this is the Boyle's idea. See, every point you have to observe very carefully. According to Boyle's idea, volume and pressure are inversely related. This proportionality is made into an equation by introducing a proportionality constant. That proportionality constant is V is equal to C into 1 by P, or I can write PV is equal to a constant. So according to Boyle, if I plot volume in decimeter cube and the pressure in atmosphere, I will be getting a graph like this. So this is how the pressure and the volume are related, which can be represented graphically like this. And then another scientist called Charles, he said the constant that is introduced here is a function of a temperature. See, I have put a small t here. Normally for temperature, we write a capital T. Why I have given small t here? I am going to introduce the temperature in a different scale at the end of this slide, where I am going to use the capital T. So in order to make a distinction between this temperature scale and another scale of a temperature, I have put a small t over here. Even in the textbooks, it is written like this. So this constant C is a function of a temperature. What is a function? Function is a mathematical rule by which two numbers can be related. How we are going to relate the constant C and the temperature? See, this relation can be algebraic, can be trigonometrical, can be exponential, can be logarithmic. So whatever may be the fashion in which these two numbers can be related. But in general, we can say this constant C is a function of a temperature. Therefore, Charles, he plotted the volume, taking it along the y-axis in the units decimeter cube, and the temperature along the x-axis. So he got a straight line, and the intercept, this point, is giving the value V0, which is the volume of the gas at 0 degrees centigrade. That is V0. Actually, this line has a slope also. That is what was discussed by Lussac, another scientist. According to Lussac, he related the temperature and the volume at a constant pressure. He maintained the pressure constant and related the volume and the temperature. And he said that volume is a linear function of a temperature. You know what is a linear function? It is exactly like the straight line proposed by the Charles. As it is a linear function, the linear function can be written like this. V is equal to A plus BT, where A is the intercept. You know the equation for a straight line, y is equal to mx plus c. Y is a variable, x is a variable, where m is a slope and c is the intercept. Only thing is the equation is written in a different order. So this A is V0, that is the volume of the gas at 0 degrees centigrade, and B is the slope. What is the slope? Slope is dy by dx. dy is equal to dou V, the change in the volume, and dx is the change in the temperature. What is the volume change per unit change in the temperature? That is the slope. Therefore, the same equation can be rewritten like this. Volume at any temperature is equal to volume at a 0 temperature plus the change of volume with a change of temperature at a constant pressure into temperature. So this was the linear equation proposed by Lussac relating the volume of the gas and the temperature. Let me say this is the equation number, this is the equation number 1. Now, you watch closely. I want to introduce another parameter, which is called the coefficient of a thermal expansion. Coefficient of thermal expansion is nothing but alpha 0. That is coefficient of thermal expansion at around 0 degree centigrade. Alpha 0 is equal to 1 by V0 into dou V by dou T, which means the change of volume with the change of temperature at a constant pressure. Let me say this is equation number 2. Now I am going to substitute the equation 2 in equation 1. Carefully watch. When you want to substitute the equation 2 in equation 1, volume is equal to the V0 remains as such, and instead of writing this part, I am introducing 1 by V0 and another V0. Therefore, this V0 will cancel out and you will be getting just dou V by dou T at a constant pressure into temperature. That is this term. Why I am doing this small alteration here? I want to bring this alpha 0 inside this equation. Therefore, now this part is nothing but alpha 0 into T. Therefore, the equation is rewritten as V0 into 1 plus alpha 0 into T. So that is equal to V0 alpha 0 1 by alpha 0 plus T. This is also small t. So that is the third equation. Now, if you carefully look at the behavior of the alpha 0, for all gases, alpha 0 approaches the same value at pressure 0. When you go on decreasing the pressure, when the pressure becomes a 0, for all the gases, the alpha 0, that is the coefficient of a thermal expansion, approaches the same value. Now, in order to change the coordinate systems, what is a coordinate system? Any point or any change in the space can be represented in terms of distances and angles. Suppose if a point in space can be represented as 3 distances from the origin, then it is called the Cartesian coordinate system. So all these things are the coordinate system, and other things I will discuss when I teach you the quantum mechanics. After the completion of the biophysical chemistry in the physical 2, I will be immediately starting the quantum mechanics. So in the quantum mechanics, we will be discussing in detail the coordinate system, the Cartesian coordinate system or the rectangular coordinate system, spherical polar coordinate system, cylindrical polar coordinate system, how a small volume element can be expressed in all these coordinate systems we will be discussing at a later stage. Now, in order to change the coordinate system, a new scale of temperature is formed, which is called the ideal gas scale of temperature. What is that ideal gas scale of temperature? I want to take this entire unit from the equation 3, that is 1 by alpha 0 plus the small t temperature, which is equal to the capital T, which is called the ideal gas scale of a temperature, which is equal to 1 by alpha 0 plus T, where this 1 by alpha 0 for any gas, because the alpha 0 approaches the same value at a pressure is equal to 0. It approaches the same value for all the gases, and which is equal to 273.15 degrees centigrade. So this is how we have obtained this equation. Temperature in the absolute scale, ideal gas scale of a temperature is also called the absolute scale in thermodynamics, which is equal to 273.15 plus the temperature measured in Celsius scale. Therefore, the equation now becomes a volume is equal to alpha 0 V0 into T, the capital T. I suppose you understand the points discussed in this slide, which is the given the equation number 4. Now look here, according to Boyle's law, what's Boyle's law? V0 is equal to C0 by P. Actually, what we have said, volume and pressure are inversely related. I have simply introduced the zero value here. So this is the constant, proportionality constant, and this is the volume at zero temperature, 0 degree centigrade temperature, which is V0 is equal to C0 by P. Therefore, volume, according to the equation number 4, what we have discussed in the previous slide, V is equal to alpha 0 V0 into temperature. So I can write the V0 can be taken from the Boyle's law. Therefore, this equation becomes C0 alpha 0 T. Instead of V0, I have written C0 by P. So volume is equal to C0 by P, then alpha 0 T. Let me say this is equation number 5. But actually, if you look at the C0, C0 depends upon the quantity of the gas taken. That is the mass of the gas taken. So the C0 is directly proportional to weight of the gas. And also I can introduce one more proportionality constant. C0 is equal to BW. So now I am going to introduce this BW in the place of C0 in the equation number 5. Therefore, equation number 5 becomes V is equal to B alpha 0 W T divided by P. This is equation number 6. But each gas has different values of B. I may say that the alpha 0 approaches the same value for all the gases at P0. But the constant B, it changes for every gas. Therefore, mass at T0, P0, V0 condition is M, the molecular mass, which is equal to, this is 1 by C0. That 1 by C0 is B alpha 0, P0, V0 into T0. So this is what we have got. This is equation number 7. So this P0, V0 by T0 is universal gas constant R. Therefore, in this place you can substitute R and you can relate mass with R. M is equal to R by B alpha 0, or I can write B is equal to R by M alpha 0. So now what I am going to do, I am going to substitute this B value in the equation 6. Therefore, I am getting volume is equal to R by molecular weight into alpha 0 weight, temperature by pressure. This alpha 0 can be cancelled. Therefore, what you are getting is W by M RT by P. So if you take this P on the other side, you are getting PV is equal to W by M RT. W is weight of the gas, M is the molecular weight of the gas. Weight by molecular weight will give you number of moles of the gas. Therefore, PV is equal to nRT. So this is ideal gas equation. So this is how the ideal gas equation was derived. So the ideal gas equation actually, it contains the 3 equations proposed by 3 different scientists. I want to go back to the slide, the previous one. So it contains the idea of Robert Boyle, it contains the idea of Charles, and it also contains the idea of Lussac, And the understanding of all these three people and their graphical representations, putting everything together and also changing the coordinate system, and we have arrived at this simple equation PV is equal to nRT. Actually, it is very simple to say that PV is equal to nRT. But if you keenly look into the philosophy of this equation, that involves so much of understanding. This is called the ideal gas equation. And according to Avogadro's understanding, he said equal volume of a gas at the same temperature and pressure, equal number of molecules were observed. Look here, if you take all the gases, equal volume, the same temperature and the same pressure, the number of molecules present in all the gases will be the same. So that number he called the Avogadro number. Suppose if you take 32 gram of oxygen, it contains Avogadro number of oxygen molecules at 0 degree centigrade and 1 atmospheric pressure. If you take hydrogen, 1 molecular weight at 0 degree centigrade and 1 atmospheric pressure, that will also contain 1 mole of the substance. And the people calculated the volume, they got 22.4 liter is the molar volume of any gas at 0 degree centigrade and 1 atmospheric pressure. See, we have already discussed what is a molar volume in the previous class and how this molar volume was found out. Now, if you substitute, look here, I have already told you what is R. P0, V0 by T0. P0 value we know it is 1.01325 into 10 power 5 Pascal into molar volume we know it is 22.4 into 10 power minus 3 meter cube per mole. I am substituting in the SI unit. It is 22.4 into 10 power minus 3 meter cube per mole divided by temperature in the absolute scale, it is 298.15 Kelvin. If you substitute these values, you are getting 8.314 Pascal meter cube per Kelvin per mole, where the Pascal meter cube is joule. Therefore, it is 8.314 joule per Kelvin per mole. So, this is how the value of the universal gas constant R was calculated. Actually, we have seen this universal gas constant in a different manner. Look here, this is also the same idea. Work done per degree per mole. What is the work done when you change the pressure and the volume? And the same idea was taken according to the heat capacity of the gases also. See, one particular constant discussed in 3 different manners. When you are taking 1 mole of a substance in a container, a gas, you are trying to increase the temperature of the body by 1 degree. What is the quantity of the heat energy supplied? You are getting 8.314 joule per Kelvin per mole. So, the universal gas constant is discussed in different types. You look here, we calculated what is the molar volume of a gas. So now we have taken a different approach and we have arrived at the same constant 8.314 joule per Kelvin per mole. So this is how the ideal gas equation was derived and the value of the universal gas constant was established. So in the next slide, we are going to discuss a little bit the thermodynamics of the ideal gas. Many of the things I have taught you in the second year in the thermodynamics class. But now you have to pay a little more attention because we are looking the same ideas in the view of an ideal gas. So look here, pressure, temperature, volume, and the number of moles. Actually, here I have replaced the mass by number of moles because we have changed our approach to the number of moles. It is weight per molecular weight, weight divided by molecular weight. So among the 4 physical parameters, pressure and temperature are intensive properties. I've already told you what is intensive. Volume and number of moles, extensive properties. Actually, intensive properties and extensive properties, according to thermodynamics, we have seen in a different fashion. But in the gaseous state, suppose I am taking a container and I am subdividing the container into several small parts. And if I am able to sum up all the values of the parameters in each subdivision, and the summation of them gives the value of that parameter in the entire system, then it is called an extensive property. Look here, I take volume, volume here, volume here, volume here, volume here. If I sum up, I am getting the total volume. I take the number of moles. What is the number of moles of the gas found in this subdivision? Number of moles in this subdivision. If I sum up everything, I am getting the number of moles in the entire system. But if you take the pressure, if I take the pressure here, if I take the pressure here, if I take the pressure here, if I sum up all pressures, that is not equal to the pressure of the total system, because the pressure of the total system is the pressure of any subdivision. You need not sum up. Similarly, temperature. What is the temperature here? What is the temperature here? Everything is the same. That is the temperature of the total system. So if you are not able to do that summing up of the value of the variables in the subdivision, then that property is called intensive property. If you are able to get it by summing up, then that is called extensive property. In thermodynamics, we simply say that intensive properties are independent of the quantity, and the extensive properties are dependent on the quantity of the substance. But in the gaseous state, we are discussing the same point in a different fashion. So look here, number of moles is equal to the weight taken by the molecular weight, whereas volume is equal to weight taken by molecular weight into RT by P. What I have done, I have simply rewritten the ideal gas equation. Now, I can write PV bar. What is this V bar? V bar is volume divided by number of moles, which is the molar volume. What is the volume of 1 mole of a gas in this standard condition? Molar volume. That is called V bar. So, here the volume is an extensive property, but V bar is an extensive property. Look here, V bar is an extensive property. So volume is extensive, but V bar is intensive, because this is something like this. Weight is extensive, but density is intensive, because density we take weight per volume. Therefore, density is intensive property, but weight is extensive property. Similarly, volume is extensive property, but V bar, the molar volume, is an intensive property. So you should understand this particular point. Therefore, I can write PV bar is equal to RT. So all intensive properties, they are, some of them are dependent, some of them are independent of each other. So look here, I'm going to draw the isotherm. What is isotherm? Isotherm means keeping the temperature constant. I'm going to plot pressure expressed in atmosphere and the V bar expressed in decimeter cube per mole. So look here, for a particular temperature, say 122 Kelvin, I am getting a graph like this. For when I change the temperature, see, I am not varying the temperature, I am maintaining the temperature constant, but the same graph is plotted for different temperatures. That is the understanding. So I am maintaining the temperature constant, I am plotting the pressure versus volume. I change the temperature and maintain the temperature constant. At 312 Kelvin, I plot the pressure versus the V bar. Similarly, for a different temperature, it is plotted and you are getting graphs like this. And this is called isotherm because temperature is maintained the constant. In another graph, I am going to maintain the pressure constant, isobar, and I am going to vary the temperature and note down the volume change. Say, when I maintain the pressure at 10 atmosphere and a constant, I am getting a straight line like this. 5 atmosphere, I am getting a straight line like this. 4 atmosphere, I am getting a straight line like this. 2 atmosphere, I am getting a straight line like this. So this is isobar. Similarly, when I maintain the volume constant, that is called isometric. When I draw the isometric, I plot the pressure expressed in atmosphere and the temperature in Kelvin scale. For 10 decimeter cube per mole, I'm getting a straight line like this. For 20 decimeter cube per mole, I'm getting a straight line like this. For 30 decimeter cube per mole, I'm getting a straight line like this. So from these three different studies, isotherm, isobar, and isometric, ideal gas is a gas which assumes zero volume at 0 Kelvin. And also for an ideal gas, volume is tending towards a zero when pressure is tending towards infinity. Look here, in these two things, when volume becomes a zero at 0 Kelvin, and also volume approaches a zero when pressure approaches infinity. So what is a real gas? At a low temperature and high pressure. See, when pressure is high and temperature is low, volume becomes zero for an ideal gas. But for a real gas, at a low temperature and very high pressure, liquefaction takes place. The gas becomes liquid. When it becomes liquid, there is no appreciable further change in the volume. Therefore, volume is not approaching zero, but volume approaches a small quantity, and further reduction in temperature or further increase in the pressure is not making appreciable change in the volume of the gas in the case of real gases. And also in the case of isotherm, at high pressure, when you increase the pressure high, again the liquefaction takes place. After the liquefaction, there is no appreciable change in the volume. Therefore, in general, I can say an ideal gas is the gas whose volume becomes zero at a 0 Kelvin and whose volume is tending towards a zero when the pressure approaches infinity. But in a classical understanding, I can say ideal gas is the gas which does not have intermolecular forces, and a real gas is a gas which has intermolecular forces. Now I will disconnect and please reconnect for further studies.